Hello, everyone. We are back into a theme webinar today. And today I have two speakers that are two of our theme ECRs. I will introduce Dr. Anthony Roccisano, who is a postdoc with me here at University of South Australia. And the other speaker will be Dr. Patrick O'Toole from RMIT in Melbourne. And they are both going to talk about laser metal deposition, and they're about process parameters and defect detection. So laser metal deposition is an advanced manufacturing technique, and that can provide solution for additive manufacturing, repair, and product improvement for a variety of industries, such as the mining industry, agriculture, and defense, and many, many more. As systems and processes mature, the likelihood of defects formation decreases. However, the risk of critical defects that threaten the integrity of the part necessitate post-production inspection. We explore newly developed techniques that have the capability to detect defects as they occur during the manufacturing process, enabling problems to be remedied as they occur. Optimizing the process parameters can significantly improve the reliability of the process. However, testing all possible process parameters is a time-consuming and costly endeavor. Using computer modeling, process parameters combinations are evaluated prior to conducting experimental testing, and thus reducing costs and time of build optimization. This is what you're going to hear today. So I'm first going to introduce the second speaker. Yeah, this will be Patrick O'Toole. Patrick joined CEAM and RMIT as a research fellow this year in 2021. And to develop a model of laser metal deposition and apply it to high-speed laser cladding, and to develop a model integration to predict hot cracking in 3D printed parts. Prior to CEAM, Patrick worked at Cyro, where he developed a multi-scale model of solidification of aluminum silicon alloys. Patrick has also worked at the University of Melbourne in collaboration with UNSW Engineering and DST Group to develop scale bridging, microstructure, and crystal plasticity methods. He has a bachelor degree in chemistry from University of Sydney, and he obtained his PhD also in Sydney and Venice, specializing in computational chemistry, mesoscale particle simulation, and free energy methods. So this will be our second speaker. And now I want to introduce Anthony. Dr. Roccisano has been now with us for the beginning of this year, also in a new ECR within CEAM. And his research strengths include materials characterization, electrochemical analysis, and mechanical design. Anthony's research interests include laser metal deposition for wear and corrosion resistance, and laser metal deposition process optimization and control. Anthony has a Bachelor of Mechanical and Aerospace Engineering from the University of Adelaide, and he received his PhD also from the University of Adelaide in 2020 from the School of Mechanical Engineering. Yeah, that was it from my side. I will join you later again for some Q&A. And now I wish everyone a lot of fun with our two speakers about laser metal deposition for process parameters and defect detection. I give over to Anthony. Goodbye.
Thanks for that, Christy. Like Christy said, I'm the new ECR at UniSA, and I'd like to give a quick presentation on defects and detection methods in laser metal deposition, or LMD. So for those who aren't familiar with laser metal deposition, I'll first give you a bit of background. Laser metal deposition, LMD, is also known as laser cladding and others in different parts of the world. Basically is a welding process which utilizes a laser heat source to weld feedstock materials to a substrate. Primarily it uses a powder feedstock, although there is some limited wire usage around the world. You can differentiate different LMD systems based on the nozzle design. Two common ones are off-axis LMD and coaxial LMD. They're both essentially the same, they produce the same parts. It's just that an off-axis LMD system has the powder flow and the laser coming from different nozzles versus the coaxial where they're coming from the same. So this brings us to how LMD actually works, what's the deposition strategy. Like most welding processes, you form single tracks of weld deposited material. For LMD, you typically want to cover areas. So to do that, you overlap these tracks, which forms a relatively uniform surface. When you want to bring your parts up to a more 3D type dimension, you overlay these tracks on top of each other to build up a large 3D structure. In terms of applications, LMD is essentially an additive manufacturing process. How you use it is up to you. You can use it for straight additive manufacturing, where you can produce parts which are typically produced through conventional manufacturing, or you can use it for repairs or adding wear and corrosion resistant coatings. In terms of repair, worn parts such as industrial shafts, they typically wear on the bearing surfaces over time. Instead of throwing out that entire shaft, you can just repair the worn areas and bring it back to tolerance. In terms of wear and corrosion resistant coatings, if you have parts such as brake discs, for instance, to improve the wear and corrosion resistance to decrease the amount of particulate production, you can coat this with a wear or corrosion resistant coating. That's one of the key advantages of LMD as a process. It's compatible with essentially all metals and metal matrix composites, and it bonds that to the surface with a metallurgical bond instead of something like a mechanical bond. You can have quite low dilution once you get your parameters correct, and you have a very wide range of applications, like I said, for corrosion resistance, wear resistance. The main disadvantage with LMD though is, I guess, something which is a disadvantage with most advanced manufacturing processes, is that it has quite a high cost. The laser sources, the CNC equipment, such as the robotic arms, are all quite expensive, although this has come down in price recently, which has seen high proliferation of this technique. In addition, as it's quite a welding process, the parts aren't finished. If you want to have a perfect bearing surface, you need to apply additional manufacturing to it. And I guess this brings us to the crux of this topic, which is this process can be susceptible to defects if our process parameters are not optimized. Now, what are the process parameters we're talking about? LMD is quite a complicated interlay of different parameters which give you your final part. The most common ones which have the biggest effect on your quality are the power, which is the actual power coming from the laser, the scanning speed, or how fast that laser goes over your substrate, and the powder feed rate, which is essentially how much material you're putting into your melt pool. All these parameters are interlinked, and if you have a good parameter which is giving you a good cladding or a good coating, and you want to, for instance, increase your scanning speed to increase your production rate, you need to try and balance the other parameters. In literature, you can look at different ratios such as the area or global energy density, which shows that if you increase your scanning speed, you also have to inversely change your power. There are many other parameters I haven't touched on, such as what shielding gas you use, what flow rate you're using, what laser wavelength you're using. But I'll focus on the top three and just give you a little bit of insight on how changing those affects your quality and the parts which you produce. In terms of the laser power, you can see as you increase your power without adjusting the other parameters, you can end up with a higher dilution, a wider melt pool, and you end up with a part which isn't quite right for you. You increase your scanning speed, for instance, without adjusting how much laser power you're putting or adjusting the material feed rate, you can see that the deposited track narrows significantly, and it ends up being a very thin coating. In some applications, this is highly desirable, but in others, it isn't. So it's something that you need to balance. The powder feed rate is probably the most common and the easiest way to think about it. As you add more material to your part, to your melt pool, the bigger your melt pool is and the bigger your deposited layer is. Now, something to consider is that you don't typically manufacture parts using a single track only. It's all interlaid with overlaying multiple single tracks. So when you want to get high quality parts, you can't just rely on this kind of window experiments. This brings us to the defects and common defects which are found in laser metal deposition. If you don't get your parameters correct, some of these or all of these defects can be found in your final product, including hot cracking, lack of fusion, porosity, spatter, distortion, interfacial cracking, or even over dilution. If we look at hot cracking briefly, I know Patrick will go into this in more detail. Hot cracking is essentially a solidification defect. If your heat input is either too high or too low, during solidification, the transient strains in the melt pool, it can't be resisted by the material which is solidifying, and you end up with cracks. They typically occur perpendicular to the direction of your build-up, to your direction of cladding, and it's typically in the center. To mitigate this, you need to adjust your parameters, which can be a costly and time-intensive process. In some instances, you need to increase or decrease your laser power, and in others, you need to adjust the substrate preheating. In other cases, we haven't mentioned it yet, but some materials aren't exactly compatible with each other and promote cracking. In order to mitigate that, sometimes you need to use a buffer layer or a material which is compatible with both the substrate and the coating to prevent this kind of hot cracking. Other common defects which you'll find in LMD deposited parts is inclusions. Typically, silicon oxide particles are dispersed quite widely throughout your part. They're usually very small, in the range of 0.05 to 15 microns. And while they don't typically negatively impact your strength, if you have excessive amounts of them, you will see that your elongation will suffer and you won't have such a well ductile part. The way that these particles form is because there is excess silicon or oxygen in your powder feedstock. If you want to get rid of this as much as possible, you need to lower the amount of oxygen and silicon in your feed material. In other cases, your shielding gas might not be sufficient to prevent oxygen ingress, in which case you need to adjust your shielding gas, although it's more common for it to be due to the material. Another common defect which you'll find in laser metal deposition when your parameters aren't correct is porosity. You typically have two different types of porosity, a lack of fusion or a keyhole spherical porosity. Now these two tend to be mutually exclusive in that lack of fusion porosity occurs when you have not enough energy input into your parts, whereas keyhole or spherical gas porosity happens when you have too much. Once you increase the amount of energy going into your part during your deposition, after a sweet spot where you see basically minimal porosity, as you keep increasing the energy, you start to fuse your parts sufficiently so the irregular pores go away, but then you start to get gas entrapment from either your shielding gas or selective evaporation. In both cases, it just means that your heat input is incorrect and that needs to be adjusted. The last defect I'll talk about is over dilution, which in some cases is a defect and in other cases it isn't that critical. Over dilution is essentially known as penetration in more conventional welding, but it's essentially the amount of mixing between your substrate and your deposited layer. As you can see in the image below, you have quite a lot of the deposited layer into the substrate below that surface. Now, in cases where you're trying to build up a highly wear-resistant coating, if you have excessive dilution, that means that you're mixing between your substrate, which isn't wear-resistant, with your highly wear-resistant coating, which basically reduces the effectiveness of your coating. In LMD, you typically have dilution levels of 1 to 10%, although this can increase quite dramatically when you have either too much power input or in some cases, a very high scanning speed can result in high dilution because you're not getting energy absorbed by your deposited material. Instead, it's being absorbed by the substrate. So what is the cost of defects? Well, the main is that you have a lower structural strength. If you have voids or cracking in your parts, you will diminish the strength and the structural integrity of the final product. In addition, if you have voids or cracks in a corrosive environment, you can provide a path for the electrolytes to reach the substrate and cause undercorrosion. This could potentially catastrophically cause the part to delaminate. In addition, if you have a wear-resistant coating, if you have defects in it, you can lower the wear resistance of the part, which essentially makes the entire process irrelevant. The main issue with this, though, is that it's expensive and time consuming for operators to test all material combinations to minimize these defects. I only showed you some of those window experiments previously, but that's a lot of destructive analysis of the parts after they've been produced. Now, the most common defect detection methods using non-destructive testing is dye penetrant inspection and magnetic particle inspection. Of course, you can always destructively test your parts for defects, but then your customer won't have a part to show. In dye penetrant inspection, it's essentially a part is cleaned and wiped free of any debris, and a dye is sprayed on the surface. This dye is absorbed into surface defects, and then once wiped off, a developer is sprayed on. This allows the defects, like the cracks in this image shown here, to come through, and you can see if you have any defects in your part. Now, this is a widely used process in LMD because it can be used on magnetic and non-magnetic materials. In addition, though, it can only identify surface defects like cracking and pores. Anything which is subsurface can't be observed through this process. In addition, the part has to be finished machined before you can do this effectively, which means that if you find excessive defects, like in this image here, you have to take all the coating off and reapply it. Another common NDT process is magnetic particle inspection, or MPI. This is typically only used in ferromagnetic materials and is very common in the pipeline industry primarily, but it can have some use in LMD. Essentially, a magnetic particle laden carrier is sprayed onto your part. Usually it's iron oxide in some kind of oily substance, sometimes kerosene. And basically a magnetic yoke is placed on your part and the magnetic field lines allowed to pass through the material. When you have any discontinuity like a crack, the magnetic field lines are deflected and you start to see the crack shown above the surface by the magnetic particles. The main issue with both of these NDT processes, though, is that you can only do this after you've finished your process. So if you've spent 10 hours coding something, only to find out that you have excessive defects, you have to start again, which costs you time and money. The latest online monitoring methods are currently being researched such that you can determine if you have any defects ahead of time. Now, this is very useful in that if you find you're getting defects, you can change your parameters on the fly so you don't get defects. There's some research into all these techniques, but I'll go through these three primarily. First of all, thermography or thermal cameras or pyrometers. Essentially, infrared cameras and pyrometers monitor the actual melt pool of your material. And anytime there's a fluctuation or a change in the temperature, that can indicate that there's defect, because if there's any gas entrapment, that will have different handling of temperature and heat flow. In terms of spectroscopy, I'm talking mainly about plasma spectroscopy. As you're depositing material, you have a spectrometer which can measure the emission lines. As you change your parameters, or if your parameters are changing and causing defects, this can cause different spectra and emission lines to occur, which you can then correlate to defects. Thermography and spectroscopy aren't as easy to directly find defects. You have to do a lot more processing, but they are both very powerful tools. Another process which is finding some great promise is acoustic emission. Essentially, you use microphone arrays to measure if you hear any defects. So if you hear cracking occur in your part, your microphone can pick that up and alert the operator that something needs to change. This is basically a process which can use either audio microphones or laser microphones, and has found some use in both LMD as well as SLM. I want to thank you for listening to my presentation. From here, I'll pass you on to Patrick, who will talk a little bit more about the LMD process, but primarily on CFD of it. Thank you.
So as I said, I'm going to talk to you about CFD, of a particular type of directed energy deposition called ultra high speed laser cladding. And this is the kind of modeling work. This is basically the modeling work that we're doing at RMIT as part of the SEAM Center. So just in reference to Anthony's talk, there are a bunch of different types of DED, and even within the space of laser cladding, there are a whole series of different classifications. And broadly, they scale with, or the classification changes with the speed of the process. So here I've got a little chart that shows the difference between conventional laser cladding, which is kind of established in the mid-70s, of, where deposition rates of up to 2 meters per minute. In the 90s, there was a development towards faster, so 2 to 20 meters per minute, where you get significant residual stress near the clad surface and a high cost of a secondary laser source. And then more recently, this ultra high speed laser cladding, which can go upwards of 20 meters per minute, uses a single laser source, and there are a couple of different configurations. But generally the set of process parameters available are not really well charted or not really well understood. There are a couple of technologies that are very well optimized, but a lot of the space is not well understood. So a kind of nutshell summary of what this looks like. Generally, you have a coaxial nozzle, powder delivery with laser. There's some meeting point where they meet, and then there's heating up of the powders, and then they're deposited on the substrate. There are 3 different configurations. We're looking specifically at the one in the middle, which is having a rotating substrate and a stationary head, or a head that moves along the beam as it rotates. But there are other configurations, such as a rotating substrate, which has another kind of set of configurations required that could be optimized for. Now, this is kind of what it looks like, and this is excited that it won't play my video. Anyway, I'll just move on. So our aim is broadly to develop a process model using CFD for this fast process. We want to calibrate it to carefully matched experiments. We then want to explore the parameter space to find new cladding configurations. What I mean by new here is basically efficient cladding configurations, whether it be particularly fast, particularly thick, particularly thin, or having good mechanical properties, or eventually having good mechanical properties. And the idea is here to do this in such a way that you don't have to go through the loop of experimentation, which can be extremely expensive and time consuming. So using this, we then want to direct our experiments so that we can eventually produce parts that leverage the information developed using the model. So the components of the model are basically 6 things here. There's heat applied from a laser. There's the heat evolution of the material, so it warms up, undergoes some phase transitions of both the substrate and the powder. Sometimes either or both. Sometimes the substrate, it's desirable to have some penetration, sometimes it's not. We need to have some way of evolving the molten portion, and the molten material and its heat evolution, or I should say its mass transport, also affects the heat evolution of the material. Then we have some description of the nozzle itself, the delivery of powder through the nozzle and how it interacts with the laser, and then some set of predictions. Okay. So you might think that this is something like a digital twin, and you could possibly call it a digital twin. Really, it doesn't really fall under the strict definition, which is, some not really looking at the process itself, but having some kind of numerical background, real-time process that happens. But what you see is, what you tend to find is that it mirrors the experiment almost exactly, with a few extra steps. So we have some, in an experiment, you start with your material, you have a process that you subject the material to, and then you have this analysis, and you can understand some process here as the details of your process. Then in a simulation, it's very similar, except that your material is described by a set of thermophysical properties that are specific to the material. Then there is a setup and a solver, which is a kind of mimic for the process. And then you have these post-processing where you analyze the results of your simulation. In our case, the first step is done in software by thermophysical properties software called JMAT Pro. And then the last 3 steps are all performed in a software suite called Flow3D. So what that looks like when you have a digital material is you calculate these thermophysical properties. You need to have some way of refining the data, otherwise you have these huge amounts of data. All of these blue points on the right, this is for a particular material, and these are all of the, or most of the input properties that you have. So density, thermal conductivity, viscosity, surface tension, and heat capacity. And we refine this data down by describing parts with high variability, with large numbers of points, and small variability or linear variability with variation, I should say, with more sparse data. And that's basically what a material is. It's kind of a funny representation, reducing it to a bunch of numbers. For the molten pool physics, we make some assumptions about the molten pool. So generally we say that the flow is Newtonian and laminar, where we conserve, the conservation is expressed, energy is expressed in terms of the enthalpy. And so we convert between enthalpy and the temperature. The enthalpy is temperature dependent itself, and the amount of liquid, and therefore the material properties, is solely a function of temperature. So we're often dealing with a 3-phase system with laser metal processes. You find that you start with a solid, you heat it up with the laser, you get some liquid formation, and then if it's hot enough, you'll get vapor formation. And these situations all contribute to the evolution of your of the system. The CFD method that we use uses something called the volume of fluid approach, where you track this free surface with like an approximation, a numerical approximation of how much fluid there is. So here I've got a gaseous phase and a liquid phase, and then there's cells that are partially filled with liquid. I should say fluid, really, because the fluid here is not just the liquid, but is also the solid. And we account for the presence of the solid and the liquid with another metric. Then we have a couple of momentum and mass source terms and enthalpy source terms, which I'll go over in a sec. So the momentum source terms here are things like surface tension effects, which affect both the curvature, which can lead to balling, large pool aspect ratios, and also drives flow within the melting pool. And this is the much spoken about Marangoni effect in the driving flow inside the molten pool. There's also some flow resistance in the mush due to the presence of the solid. So when I mentioned before that you have one fluid with a free surface, within that fluid you have a solid component and a liquid component, and the solid effectively has an infinite viscosity, so it doesn't move. There's also these other common effects which need to be explored in the context of a model, such as the wetting angle. And this wetting angle exerts a force on the edges of your liquid as it contacts the material and determines its shape. So, and these also, this quantity, the surface tension, given that it changes with temperature, also has an effect on how well your material wets the surface. And the temperature difference between the two materials also affects this. In terms of the enthalpy source terms, in addition to the heat flow from the laser, there's also radiative cooling, convective cooling, and evaporative cooling. With evaporative cooling, where you have the production of vapor on the surface that also exerts a pressure on the surface, and that leads to the familiar keyholing effect that Anthony spoke about, that results often in spherical porosities. So just having a little zoom in on the molten pool here, and I've visualized this, the kind of flow lines through a moving molten pool. You can see that there's quite a lot of motion inside, and this is partially because of the tumbling of the melt pool. So the impact of the laser, which is around, which is at the front part of the pool, so on the leftmost part of the top image, you have some expansion of the liquid, and you have some solidification that goes on behind, but the pool itself kind of tumbles on itself. But then you also, inside the molten pool, you have this convective motion caused by the temperature-dependent surface tension and Marangoni, which is this Marangoni flow. The laser heat source has this representation, so we measured for a particular setup the heat flow, or rather the intensity of the laser at each point along its focal, along the focal distance, to find its approximate distribution. This is that three-dimensional representation of its energy intensity. And then we have a digital representation of that, which is to apply a Gaussian, and where we cut the Gaussian off at this region where you can reasonably say there's not enough laser intensity to increase the temperature of the material. And so what that effect has is that you have a temperature field with an increased temperature towards somewhere near the middle of the spot, a small region of which is melted, and then that goes on to form the track itself. So then we need to calibrate this model, and what we do is we run a whole series of experiments with changing the power and changing the speed, and looking at how the melt pool evolves, and we use this to calibrate our simulations to the same kind of experiments with matched parameters. And so we can look with our experimental procedure here, with our simulation procedure here, at the characteristics of the molten pool in both, here I've got it in top down and in section, with the slice through the middle, and we can get information about things like the depth of the molten pool. Everything that's yellow here is above the melting temperature of the substrate material here. And so if we increase the power, you get large, tumbling, unruly, at low speed, you get large melt pools. At relatively high speed and low power, you get almost no melting at all. But as you generally increase the speed and the power, you get these shallow, skinny, non-penetrative or sparingly penetrative laser tracks. So we can use this information to calibrate our model, and we're in the process of setting up an experiment that does this process, looking at taking two different views with two different technologies, a welding camera in one case that's illuminated by the laser light, and a thermal camera in the front part, which captures the temperature at this point. And we have this situation where it takes time to heat up a material. Once you expose it to laser light, it takes some time to heat up, and we can use this information to calibrate our model in terms of the absorbance and a couple of other things. This is the topic of an upcoming publication, but you can do basically the same thing in a computer simulation, where you can look at the rate at which the temperature increases, and you can match this to an experimental data set, and we can use that to calibrate the two things very well. And in our initial tests, our calibrations look pretty good for this particular measure. So then we have a way of representing the nozzle. So this is the nozzle that we have. Some details about the laser focus, the powder, laser powder intersection position in the substrate, and Yeah, there's also shielding gas information coming in here. It's a pretty tricky actually dealing with powder flow. There's a recent publication here that looks at the different powder flow rates on the cross sections of the powder distribution at different planes of the different planes along the powder particle trajectory, and looks at the relative laser attenuation through that. So you have, given that you have laser light coming in from the top, heating up your powder and presumably bringing it up towards the melting point, or if not to the melting point before it strikes the surface, you need to know how much of the powder is actually absorbing that light and how much light makes it through to the substrate. So once we have all of that stuff together, then we can properly implement our CFD simulation. So what we've got here is a situation where we have a small substrate that moves through space. So the whole domain kind of propagates through space. The laser, which comes in through up here, it's down. There's a point where we're generating and delivering powder, which intersects with the laser at the last possible point, and then on its traversal through the laser light, it heats up and then is deposited on the surface. Okay, an important thing to notice here is that depending upon both the size of your simulation and the relative resolution that you use, you can drastically change the time it takes to get to a solution. So generally, if you have something that's a few millimeters cubed, then if you resolve it with a relatively coarse mesh, you can have an execution time for this particular setup of 30 minutes. But if it goes down to not that much smaller, 2-3 times smaller, you have this huge explosion in the time it takes to actually simulate this. So there's a balance to be struck here. And this is what it looks like. So just quickly, I'll introduce, these are just different views. So this is a kind of orthographic projection here. This is a top-down, this is side-on, and this is from behind. Up here, the color here indicates the second material. The second material is actually the substrate. The first material here is the powder. And you'll see that everything that's yellow is something that's mostly substrate material. Everything that's green is something that's a little bit the powder material. And we're looking for this region halfway between those two values. Up here, I have this spatial heat distribution as generated by the laser. Then we have the heat flux by the laser as it's actually applied to the surface, and then a temperature field. So I'll play this. Hopefully the frame rate is good enough for you to get something out of this. So the first part, the powder is not being irradiated. We actually switch the laser on some ways into it. But you can see the powder material is being melted when you've optimized these, optimized some of these properties. And then we can use this to explore your cladding configuration. Now, this is on a relatively coarse mesh, and so everything's quite coarse. And what you're seeing here is this yellow region is a little bit overestimated in terms of its penetration, but we can investigate the cladding characteristics using this model. I'll just play that one more time. So you can see, draw your attention up here, where the heat is actually applied is mostly as the powder hits the surface and creates generally slightly higher regions. You see those regions being heated up the most. Okay. So where do we go from here? We intend to use this model to basically optimize our deposition efficiency, and whatever that means depends on what you are trying to optimize, I guess. So maybe you're trying to optimize powder utilization or the cladding geometry itself or the bond. One of the things that we want to look at is for multiple tracks, what happens when you overlap the tracks, and can you gain some modicum of height control by playing with this combination of power, speed, and laser powder feed rate. And then we generally want to explore these cladding configurations to look at both untested parameter combinations, but also untested material combinations, given that it's much simpler to exchange your material by digital representation than by ordering it from a supplier, figuring out a new set of parameters to weld it or to deposit it, and then carry those out and do the whole experimental procedure. If we can do that purely in on a computer beforehand, then we can get some idea about whether or not a particular combination with a particular combination of parameters would be useful. Thanks very much. There are a couple of people with whom I work directly. Ricky Wu is a PhD student at RMIT, Professor Milan Brandt and Professor Marchian, and Associate Professor Andrei Molotnikov, Neil Matthews at RUAG, and then a couple of people at Flow3D for giving support, Pari and David, and then of course all my SEAM Center colleagues, not the least Anthony. Thanks.
Okay, thank you, Patrick. Thank you, Anthony, for the interesting talks. And it's also good to see that people were already asking questions in the Q&A section. And yeah, I don't have. I also have a few questions, but let's start first with the ones that we already have in the Q&A. And if you have any more questions that you are just coming up with now, just type them please in the Q&A section. And I will then read them out loud, and then Anthony and Patrick can answer them. So I will start with the question from Annelies, and this is for Anthony. Is there research being conducted to combine thermography, spectroscopy, and the acoustic emission to detect defects, specifically maybe in the research space?
In terms of combining all three of those techniques, I haven't seen much where they're combining multiple techniques. It's fairly new, most of them, so they're trying to do individually thermography, spectroscopy, and acoustics. But no, it would make a lot of sense to include, combinations of all three together to try and make up for any of those limitations.
Maybe I have then a question that goes in this also for your talk. How can you? So it's good to know that I have a crack, or that I have a pore. But what about sensing of the location of the pore? Is it also possible to say, okay, I have a huge pore on this and that spot?
It depends. So there is some research that we're thinking about, and we're looking into at the moment with acoustic sensors using acoustic arrays, where if you have some sort of defect, you can try and triangulate that orientation. There has been some research where using acoustics in general, they found when they sensed a defect, there was actually a pretty set offset. So if they sensed a defect, it actually occurred 2 seconds previously. You can use that with your CNC to try and triangulate where it was in your deposition strategy. So it is possible. There hasn't been much research behind it, but it is something which should be looked into in the future.
Good. But that is something we like to hear. If there hasn't been a lot of research done yet, that means for us researchers there's a lot to do. Yeah. So actually that's a good thing in that case, maybe, at least for us. Now there's a question, I think it's more like a general question, that is from Dan Lawrence. From a day-to-day production perspective, I would love to see typical approaches to reducing the defects mentioned in this presentation. Could SEAM consider such a webinar? A toolbox talk of sorts, discussing the typical ways of getting rid of porosity, decreasing dilution, the best way to increase speed and layer thickness. Maybe I can try to give an answer there. I think like a really basic laser cladding, laser deposition welding talk might be a good idea. So I think that's something we can think about, and maybe we're going to present that next year for everyone who is not even so deep into laser cladding yet, to give a little bit even more of a ground approach there. Yeah, then David asks, on an actual component with laser and or substrate movements, how do you ensure that you get enough penetration dilution to get a metallurgical bond when you add filler material into the beam? How do you compensate for this? Maybe I would give that to Anthony. Yeah.
Sure. So on an actual part, this all goes back to where we mentioned that when you're trying to look at your parameters, you need to do a lot of testing. So in most production cases, if you have similar materials, you'll have to do different deposition trials and see if you get effective penetration in your part. From there, you can do, if you have the time and the money, you can do actual destructive testing of your parameters to test it, but that's quite rare. You typically just have to try and adjust your parameters in testing to make sure you get adequate penetration.
Thanks. And now for Patrick. Again, in the analyse, can your model accommodate the introduction of high melting point particles into the melt pool? Particles such as tungsten carbide, etc., and how will it affect flow in the melt pool? Well, that's an interesting one, because the tungsten carbide, you don't want it to melt, and in most cases it shouldn't melt, at least not before it hits the melt pool.
Yes, that's a great question, and at present the answer is no. And the only reason is due to the software. What Flow3D have done is they make a for this two material model. So we're actually depositing two different materials. Sorry, one different material onto a substrate material of another kind. And so the way they do that is through it's not a two fluid model. It's a single fluid, but they have a marker. And so depending upon what marker is there, or what the value of that marker is, it has a different combination of those two different materials. So in principle, yes, you can do that. You can do multi-phase flows. The problem is not so much with the principle, it's more so with the implementation. So their product is still in development, and while we would like to make our own contributions to the code base, it's slightly difficult because of licensing. So in principle, yes, we could. In practice, it may take longer than we want.
Okay, you have a few more questions. Maybe Chris is asking, how do the models relate to practice? So how close are you aiming to your experiments? Yeah.
Yeah, so it depends on what you mean by practice. So I mean, if it's not quite so easy as setting up at the moment we're looking at single tracks being deposited on a substrate. But if you want to move to multiple tracks, but you want to keep the high fidelity and have a reasonable time to execution, you either need enormous computing power or you need some very clever tricks. So, I mean, I showed on one of my slides, I think it was number 14, how our model in terms of this particular metric relates to the experimental data that we've collected for identical conditions, and it looks pretty good even for relatively coarse grid resolutions. However, yeah, there's plenty more work to be done to make sure to shore up that or reduce that difference. Yeah, ask me again in 6 months.
Okay, we will. Yeah, or Chris and me probably will. Yeah, I'm pretty sure. Okay, Annelies has another question, but they're all good ones, so I don't mind at all. So she's asking about powder. Cladding powder is relatively expensive, and some alloys are difficult to procure, import, etc. Anybody looking at the reconditioning of powder for reuse? Do you have an idea there, Anthony?
Yeah, I don't know specifics, but I do know there is quite a lot of research at the moment in terms of reuse. I think they're finding the challenges of you don't have that quality control once you're picking the powder off the machine, but there is some research looking into it at the moment.
Yeah, yeah, I would like to add in, I used to work for a powder manufacturer, and I would say, no, don't reuse it, please do not. As soon as it has seen this temperature before, it will probably be oxidized in some salts or reacted. I wouldn't. Yeah, rather get someone to build an atomizer here in Australia for all the standard alloys, and going down that path. Okay, Peter has a question for Patrick. Does your model consider multiple powders cladded at once? Meaning with a different composition and physical properties, or if you have a blend of different powders. So for example, you have maybe tungsten carbide particles together with another material. Could your model accommodate that?
I think it's possible to just include another parameter to represent a different material also in there. I guess the tricky part is, I guess this is somewhat like Annalie's question from earlier, is including high melting point particles. They at present they don't, but in principle they could. So yeah, it kind of depends a bit. The way that Flow3D also represents powder is a bit, shall we say, funny. They're not really fluid until they strike something that's fluid, and so
okay,
there's things to be done there.
Yeah. Okay. Good. Theoretically possible, but challenging. Let's put it like this. Another question for Patrick. Have you been looking at the formation of vapor during cladding? And could this maybe produce porosity? So basically boiling of a material and then maybe leading to porosity because of that?
Yes. So we don't really see a huge amount of vapor production with the particular cladding parameters that we use. There must be some amount of vapor production, but we don't include explicitly the presence of vapor. It's only included via evaporative cooling and the recoil pressure. However, in this case, the maximum temperature that we see in our simulations tends not to be too much above the melting temperature of the powder itself. And so what that means is that we're, effectively 1,000 Kelvin below the vapor temperature. So we generally don't see too much. I do think, however, there will be some present, especially in the powder stream as it's traversing the laser. But at present, the powder itself can't actually vaporize to reduce its temperature or elsewise. So there is some delicate optimization that needed to be done in order to get a stable simulation.
Okay, many questions, we like it. What are the power requirements for the ultra high speed laser process? I'm not sure, is it power or powder? I would like to hear both. Patrick, can you say something about what the power and powder requirements for the ultra high speed laser cladding process?
So we are looking at power, as Anthony mentioned, they're kind of linked to the amount of powder, the power, and also the speed are all interrelated. And so it's kind of tricky to talk about one without talking about all three, at least. And I mean, the requirements for the high speed laser process, it depends, because ultra high speed is kind of basically 20 meters per minute and up. We've been exploring, 3 kilowatts around there, and powder feed rates upwards of 10 grams per minute.
Upwards of 10 gram.
10 grams.
Yeah, okay. Oh God. You will be available for another 5 minutes after we hit 5 or 4:30 respectively, right?
Me?
Yeah, I don't know. I'm asking you. Because then I have another question. Yeah, you said in one of the first slides, yeah, that okay, you are super ultra high speed, and you say okay, it is high speed because you turn the lathe in a super high speed, and then you have the traverse of your laser, and that is then meter per minute.
Yep.
But actually, what you are interested in when you talk about production, how much volume did you apply in a certain time frame? And then in this volume, you're also talking about like how much powder do I actually inject and how much of the powder is then keeping on the part. Yeah, deposition rate and deposition efficiency are then the terms there. So how much in cubic millimeter, centimeter per minute do you apply? Is that,
Yes.
can you give a number there for a steel or a nickel-based material?
Well, we're looking at cobalt deposited on steel at the moment.
Yeah.
And without giving too much away, our efficiency, the deposition efficiency is hovering around the 50% mark. And we have powder, as I said before, powder utilization, powder flow rates of on the order of upwards of 10 grams per minute. So
okay.
Does that answer your question? I'm
Yeah.
not sure how much I should
give
away.
No, I understand. Okay, I just want to make the point that people call it ELA, extreme Hochgeschwindigkeit, there's Auftragsschweiß, the Fraunhofer term, or you call it ultra high speed, whatever. But that is only an advantage, a benefit, if you are happy with a very, very, very thin coating, on your part. If you need, for example, something for a wear or corrosion resistant application where you want to have some volume and you need at least 1 millimeter or 2 millimeter thickness of your coating, producing high speed is not good. You want to have a high volume to be applied and not many meters of the laser going over the surface. Yeah.
Sure. So I think
that's just the point I would like to make.
Just to maybe put another number there, with something like surface coverage of about 120 centimeters squared per minute, something like that.
120. At what thickness?
Can
you say what thickness you are aiming at?
Oh,
I don't want you to get into trouble.
Yes, I cannot. I don't think.
Good. Okay, good. So
watch this space.
Normally, you would probably look at 100. Maybe 200 microns. I would.
Yeah, it's on the it's on that order.
Good. Okay. Sorry about that, Patrick. We can go in a deep time the next time we are able to meet over a beer. Yeah. Good. We still have more. Oh God, we have 7 new questions. Okay, you're happy to go on. I'm trying to pick now the questions where I think that they're interested in a lot of people. Or where we can just say something regarding dilution. Are there any solutions of preventing high dilution for applications of wear? Let's say dilution of steel and copper-based coatings. Oh, God, sorry to be the smart ass here, but you can't weld steel and copper. Yeah, that is maybe number one that you have to think about, and then I leave the rest to Anthony.
Yeah, I think in those cases you might need some kind of buffer layer between the two. I'm not sure about the specifics of copper and steel, but I know that as you change your alloys, your laser wavelength can have quite a big influence on how much energy is absorbed. You might be getting a lot of energy absorbed by the steel and not much by the copper, in which case looking at different colored lasers could help. But in terms of specifics, I'm not sure I can answer that question.
Yeah. No, I think it is. There is not even one recipe, one parameter that you can just give to someone and say, okay, you're going to be fine with that. It depends on so many different things. Yeah, it is really the size of the part, the specific alloy that you have. It even will be a difference are you in Tasmania in winter, yeah, or are you in Alice Springs in summer? yeah, your cladding will be different. The parameters will be different depending on temperature and humidity. Yeah. Okay. Good. Then there's maybe there from anonymous a comment more. They would have a practical live case study and go further into parameters, defects, and solving problems in the near future. Thinking we now there, if the people want that, we can do that. Then there's Shane Kelly. My company, Arxbury Engineering in Western Australia, is going to purchase a laser cladding and robot combination for cladding mining equipment. Would any of the researchers on here be interested in testing their theories free of charge? So congratulations to buying a laser cladding system, Shane, and we like more laser cladding systems in Australia. And yeah, I think if we see, maybe we can reach out to you and see if there's maybe some sort of collaboration possible in the next few years. Yeah. There's again maybe something with a live case study. So I think we can maybe try to do that. Okay, that is a good one. That is one. Same. I'm not sure. Is it ours? No, oh, this one. Sorry. Genau. As we get maybe faster and faster in the cladding speed, will the fluid dynamics and drag phenomena start to become limiting in terms of powder placement? Is that something that you have explored in simulation? I think I can see where that goes. Yeah.
That's a great question. Often you find that in quite extreme cases, sometimes the underlying numerics become a problem. So where you go to really large speeds or you have really fast dynamics, you often need a very small time step and a very small grid resolution to resolve these phenomena, and which leads to a huge explosion in computational cost.
Yeah.
When that happens, so you know, sometimes you just have to wring your hands and think of something else. But
yeah.
I'm looking forward to increases in computational power.
Okay. Yeah, I would like maybe I think maybe leave it maybe now there. There were maybe a few more questions. Maybe we can forward that maybe if you have left your name there to Patrick and Anthony maybe to answer them. Yeah, please join me maybe in thanking Anthony and Patrick. It's the first time that maybe two of our ECRs maybe were giving presentations maybe here in the webinar. Normally that are more experts maybe that we know from the SEAM family or the chief investigators themselves. Watch the space maybe for the next talk maybe in that series. And actually the next one is coming up on the 26th of October. That is Tuesday in 2 weeks. And there we are going to hear about the second part of Dr. Andreas Wank from GTV in Germany. He talked to us, I think it was in April, May this year, about case studies in thermal spraying and laser cladding from GTV, from maybe what they develop there every day for industry customers. And he had maybe so much more to say the last time that we are going to give him now a part 2 in a couple of weeks. So please register me for that if you are interested. Yeah, that was it for today. One more time, maybe please join me in thanking Anthony and Patrick for their great talks today. And see you next time. Bye-bye.